In the last lecture, we saw what are stable LTI systems, and I also explained the condition for an LTI system to be stable. Now in this presentation, we will solve the problems, but first we will revise the condition. According to the condition, the given LTI system will be stable if the impulse response of the given LTI system is absolutely integrable. So whenever the impulse response is absolutely integrable, the given LTI system is stable in nature. Now what is the meaning of absolutely integrable? Its meaning is very easy to understand. This means whenever you integrate any signal, in our case the given signal is impulse response ht, so whenever you integrate the impulse response from -infinity to infinity and you get some finite value, then the given impulse response is absolutely integrable, and this means we are having stable linear time invariant system. So whenever the result of integration is equal to some finite value, or we can say it is less than infinity, the LTI system is stable in nature. Now we can check the given LTI system is stable or unstable by simply integrating the impulse response. Now I will explain why integration is not required in most of the cases. If you have the knowledge of energy signals, then you can solve most of the questions without performing any integration. Energy signals are absolutely integrable signals. We know this point, that energy signals are absolutely integrable signals, and if the impulse response is an energy signal, this implies the impulse response is absolutely integrable, and therefore the LTI system is stable in nature. So the only thing we are required to do in the problem is to check if the impulse response is energy signal or not. If it is energy signal, this means the given LTI system is stable, and the LTI system will be unstable if the impulse response is not an energy signal. It can be power signal, or it can be neither energy nor power signal. These points will become clear when we will solve few examples, but for now you should understand the process we are going to follow. In some of the cases, the impulse response will not be given directly. The system relationship will be given. For example, yt is equal to twice of xt. The system relationship will be given like this, and from here you can easily find out the impulse response. The first step is to perform the Laplace transform and obtain the transfer function. Once you have the transfer function, perform the inverse Laplace transform and you will have your impulse response. Now check whether the impulse response is energy signal or not. If it is energy signal, you have the stable LTI system, and if it is not an energy signal, then you have unstable LTI system. So the process is very easy. Now we will move to our first problem. In the first problem, impulse response ht is given and it is equal to ut minus 2. You already know how to obtain the waveform, so we will not waste our time obtaining the waveform. I will directly plot the waveform of the impulse response ht. The waveform will look like this. From -infinity to 0, ht is equal to 0. From 0 to 2, ht is equal to 1, and from 2 to infinity, again ht is equal to 0. You can see this signal is absolutely integrable. When you integrate it from -infinity to infinity, you will have the area under the curve and it will be equal to some finite value. So if you want, you can integrate it. You will have integration -infinity to infinity mod ht dt. It is equal to integration from -infinity to 0. You can see ht is equal to 0. So mod ht will also be 0. So we have integration of 0. In the same way, from 0 to 2 we have 1 dt plus integration from 2 to infinity, again we have 0 dt. So we have 0 plus t, the lower limit is 0, the upper limit is 2, plus 0. When you solve it, you will get 2. So you can see the result of integration is some finite value which is less than infinity. So our condition is satisfied and the given LTI system is stable in nature. But if you have the clear understanding of energy signals, you can directly say that it is an energy signal. Therefore, the given LTI system is stable in nature. It is an energy signal because it is finite duration signal, in which the amplitude of the signal is not reaching to infinity at any instant of time. So there is one important point related to the finite duration signals. I have already explained this point while explaining the energy, power, and neither energy nor power signals. The finite duration signals are never power signals. There are only two possibilities. They can be energy signal or they can be neither energy nor power signal. If you have the case in which the amplitude of the given signal is reaching to infinity at any instant, then the finite duration signal will be neither energy nor power signal. I will give you one example. In this example, the waveform is the waveform of a finite duration signal, but you will see when time t is approaching to 0 from the left side, the amplitude of the signal is reaching to infinity, and when t is approaching to 0 from the right side, again the amplitude of the signal is reaching to infinity. So this is the example of neither energy nor power signal when the signal is finite duration signal. The other possibility is the energy signal, and in case of energy signals, the amplitude will not reach to infinity. Like in this case, it is not reaching to infinity. Therefore, ht is an energy signal in our first problem, and we have the stable LTI system. The stable LTI system. Now we will move to the next problem, the second problem. In the second problem, impulse response ht is given and it is equal to sinc t. We already know the waveform of sinc function. From the waveform, it is very much clear that sinc function is an infinite extension signal. It is an infinite extension signal. Now whenever we have infinite extension signal, there are three possibilities. The first possibility is that it is a power signal. The second possibility is that it is an energy signal, and the third possibility is that it is neither energy nor power signal. Now whenever you have the peak amplitudes or peak amplitude decreasing in nature, it is energy signal. In this case, if you focus on the peak amplitudes, you will find they are decreasing in nature. Therefore, ht equal to sinc t is an energy signal. Now whenever the peak amplitude or peak amplitudes are increasing in nature, the given signal is neither energy nor power signal, and whenever the amplitude is constant, it is power signal. These points I have already explained in the earlier lectures, and you can see it is very easy to find out if the given signal is energy signal, power signal, or neither energy nor power signal using the properties I have explained. So according to the property of infinite extension signal, we know the impulse response is an energy signal, and therefore we have stable LTI system. So this is all you have to do in the problem number 2. Now we will move to the third problem. In the third problem, I have taken the impulse response as a periodic signal. It is equal to sine t. Now it is very easy to find out whether it is an energy signal or not, because we know the periodic signals are never an energy signal. Whenever we have the periodic signals, there are only two possibilities. The first possibility is that it is a power signal, and the second possibility is that it is neither energy nor power signal. It can never be energy signal. Therefore HT is not an energy signal. Therefore it is unstable LTI system's impulse response. We have unstable LTI system in the third problem. Now I will explain how to find out if the periodic signal is power signal or any NP signal. Whenever the periodic signal is there and at any instant of time you have the infinite value of this signal, then definitely it is neither energy nor power signal. For example, tan function. If you are having the impulse response equal to 10t, then you will see on your screen the waveform of tan function, and you will find when t is approaching to pi by 2, the value of signal is increasing, and when t is equal to pi by 2, the value of signal is equal to infinity. Therefore, there are multiple instances of time when the value is reaching to infinity. However, it is a periodic signal. But as its amplitude is reaching to infinity at multiple instants of time, it is neither energy nor power signal. And the periodic signals in which the amplitude does not reach to infinity at any instant of time, they are power signals. For example, sin t, its value is between -1 to 1. Therefore, it is power signal. But to find out the stability, we only have to focus on the energy signals, and periodic signals are never energy signals. So we have the answer, and if we have HT equal to 10t, in this case also, the LTI system is unstable because we have the periodic signal, and periodic signals are never energy signals. So we have unstable LTI system when impulse response is equal to 10t. Now we will move to the last problem, and the last problem is homework for you. I will call it the fourth problem. In this problem, the impulse response HT is given, and it is equal to RT, where RT is the unit ramp signal. The answer is very easy. The only thing you need is the understanding of energy, power, and neither energy nor power signals. So this is all for this lecture. The last problem is homework for you. Once you have your answer, comment below. I will end this lecture here. See you in the next one.